Hi, this is Alex Paulton. I'm here at the PCIM show in Nuremberg, Germany with friend of the show, JC Sun. How's it going, JC?
Very good, thank you.
Well, you know, we're here at the Bs&T booth, and, well, obviously we're talking about test here because, well, there are a lot of challenges to the engineer today, right?
Nowadays, there are a lot of challenges for electronic engineer for the power efficiency, for the power density. What people are asking for is much more wide band gap applications for the silicon carbide driven applications, but also for the gallium nitride driven challenge. The most of things is it's obvious that people have this design tools. The most difficult things is magnetic components, because this is non-linear and it's created losses, and these losses need to be improved. And then the next question is just how to test these, and the testing should be comparable in each other. And this is something we are going to bring on the show.
Excellent. Well, when it comes to performance of the materials, well, right off the bat, engineers have challenges from the wide bandgap materials, gallium nitride, silicon carbide, new topologies, new ways of working. I mean, for example, you can switch DC at high frequencies, but once you start going into AC, you start having problems with your magnetics, which means you have to test. But then, how do you test? You can't just attach electrodes and hope something happens.
Excellent. This is excellent remark, because in the classic way people are doing with the AC loss testing, but this Tesla time is going over. The Edison is coming back. That means the DC excitement, this is actually give the real loss values people need looking for. And therefore, as you mentioned before, if the frequencies increase, people are looking for what happens at megahertz for that area. And it's difficult because the thermal equilibrium is not given. So the concept is much more to shifting from the classic way to testing magnetic materials to the modern way. So I want to maybe to show you. Well, in the past, people testing this with a sinusoidal way. This is how people specified. But the application engineer, what they are looking for is much more what happens if that power semiconductors is in the gallium nitride conditions. This is what we are going to present this year. This is very new about BsT-square. BsT-square means in the square excitation, and that's the flux density is not suitable anymore. People need to split it down to the voltage and pulse width to microsecond. This is something which we promoted, or we exhibited for first time in this show. And there's a lot of resonance from the people who are interested in that.
Well, I mean, I'm imagining it's addressing a lot of problems. What are some of the application spaces that you really see getting a benefit from this technology, from these testing procedures?
Well, I think that the power semiconductor performance is improved. People know this, but the effect is that the application is not very widespread. Well, I mean, I'm talking about the gallium nitride. And the problem is the high frequency materials. If people usually think about do we need new innovative materials, and then they're waiting for the material scientists. Or there are a lot of people saying, look, we need just to optimize something, or we'll get it done. But these two questions can be eliminated if the people seriously testing and the real condition as it is. And the problem gets solved. And other than the silicon carbide is very well allocated in the power map, and therefore the silicon carbide has a requirement. For instance, on the ferrite material, it's just like the largest BS material. This is something the material which is developed for silicon carbide application, and the same trend is going to be applied also for the gallium nitride.
Well, and actually that's very important, because part of the reason that silicon carbide and gallium nitride are taking time for adoption is the engineers want to know more about the performance of the system, and not just the devices. They want to know everything, the passives, the magnetics, and they're just finding that out now. And so they need to have this information to properly design the system for optimum performance.
Right. I think that's this is also a very important point that you attach. People nowadays, they're doing simulation. The simulation concern, as far as concerned magnetic components, there just consists of copper and iron. And copper is a linear problem. It can be solved analytically very elegantly. The problem with the loss, this is something people tries to do with piecewise linearization. It sounds good, but it's difficult to apply. And what people can do is just reading the loss map, and then to apply to read the exactly measured value of the loss and apply to the simulation. That's accelerate the virtual prototyping, and that would be excellent for the future electric engineers to do the job.
Now, JC, what kind of support do you offer the engineer? I mean, a lot of this is going to be at the edge of their experience or new territory for them to explore. How much assistance do you give them in understanding your equipment and making sure they use it properly?
So, what we would like to address on the visitors much more. There are classic way to testing. There are modern way to testing. The classic way is to testing materials. The modern way is to testing the Y1 components. And we provide the data and the measuring results as raw materials actually for their work. Mm-hmm. and the supporting for the testing equipment we apply the modest approach. We just give the hardware and we upload the software on the website, and people can download this. And people looking for the operation manual is just like videos, and then that's the way that we're going to approach.
Excellent. And where can they go for the information? The URL is.
Well, we are dealing with power loss. Therefore, our website is www.powerlosstester.de. So we are from Germany. We're dealing solely with loss, and powerlosstester.de is our website. Please check more.
Excellent. Now, before I let you go, JC, do you have any last words for our audience, a final tip or advice?
So, well, I think it's very important that the magnetic components become increasingly in tension, and these can be solved if people willing, if people want, they can solve this with the tools, and it's for in good sake of power efficiency and power density.
Excellent. Well, hey, thank you very much, JC. I appreciate you taking the time, and I hope you have a great show.
Yeah, thank you very much, Alex. Thank you.